Hello everyone, my name is K. Rajesh. I am from CSC B section. My topic is about data science technologies for better software. Introduction. Data science is mandatory in today's business to capitalize on achievements and assist. This specifically holds for a modern software development where data science facilitates analyzing product, process, and usage and thus managing evolution and performance. With the convergence of embedded and IT domains such as the IoT, Internet of Things, and automotive systems, software systems are becoming more complex. Complexity has two faces. On one hand, it means more functionality and fluid delivery models, thus offering markets more value such as the ability to deliver a single customer focus. Complexity, however, also means the growth of technical depth, which slows productivity and lowers quality. As engineering generates ever larger and more varied data sets such as features usage, code analysis, test coverage, error logs, and maintenance data, companies face the challenge of unlocking the value of the data. Those, fa- those failing the effectively apply data science in their software engineering processes are increasingly putting themselves at the competitive disadvantage. Classical software measurements have played a key role in managing the complexity of software processes and products in recent decades, but in reaching its limits because of the ever increasing amount of available data and their dependencies. With embedded software becoming increasingly pervasive, pervasive and critical to a society, engineers must ensure that their software performs as intended and don't fail. Delivering defective software have many consequences. Essential steps for data mining. Data science and big data analytics are methods to systematically collect, process, and analyze a very large amount of data. Conway states that data science is the cross-domain discipline that requires in-depth basic computer science and mathematics skills, as well as expertise in the application domain. However, in practice, the term data science is often used as the buzzwords, addressing a variety of fields in expertise in different depths. One central consequence is that it is about expertise in dealing with the big data, that is, an increased volume of data, increased variety of data, and increased velocity for processing data. One of the fullest considerations of data science and related consequences can be found in the Edison Data Science Framework (EDSF). In the EDSF, a data scientist refers to a user who has enough knowledge and expertise in the areas of business needs, domain knowledge, analytical skills, programming, and system engineering to continuously advance the scientific process across all stages of the big data lifecycle to deliver an expected scientific or business benefit to an organization or project. One critical competence in data analytics is the ability to build and reliably evaluate models. In this context, a de facto standard is the cross-industry standard process for data mining, CRISP-DM. It describes six steps that are essential for data mining and is widely used in research and industry. Business understanding. Understand the business objective of the organization. Define analysis goal and step up a project plan. Data understanding. Collect, characterize, and understand the data and their meaning and analyze the quality of available data. Data preparation. Select the data to analyze, clean the format, and uh, format the data. Modeling. Choose the right technique for modeling buildings, create the model, and analyze the quality of the model. Evaluation. Evaluation and review the results and determine follow-up steps. Deployment. Plan how to deploy and maintain the model in practice. Document the outcomes and lesson learned. Data-driven quality management. Q-Rapids, a research and innovation project of the European Union, Grant 732253, aims to create a way to exploit software product, process, and usage data with data science to improve software quality. The Q the Q-Rapids architecture, as shown in Figure 1, provides scalable data ignition from heterogeneous data sources, interfaces, and data mining frameworks to derive a data driven quality models and evidence based recommendations to decision markets. These recommendations can include, for example, an alert about identified or predicted external quality problems and proposals related to quality requirements. Business understanding. There was there was much potential to improve the software by understanding runtime data. The goal was to identify within the development time of the platform the key aspects that influence software quality at runtime and to predict the expected number of runtime issues based on that. The business goals was to reduce the time and effort expect, expended exploiting runtime data and its history. Data understanding. To obtain these goals, we had external data, example access or error logs, application crashes, directly received bugs from hotlines or emails, and internal data. Example code quality matrices, quality rule violations, comments available. Based on the Q Rapids tooling, we used APEG connectors as shown in Figure 1 to ingest, um, ingest data in real time. We ended up creating and centralized repos- uh, repository with heterogeneous data, including using data. Example crashes and logs from mobile applications. Then we made an analysis on relevant features of our data as not all collected data were of interest. Data preparation. We integrated the data stored in different source systems and structures, handled, handled data quality defects, example, incomplete, inconsistent, and incorrect data, and transformed the data into the format acceptable for specific methods and tools used during the analysis. This has been the most time-consuming step. Software data are created automatically, but not for the purpose of being radially analyzed. Evaluation. Preliminary evaluation showed the ability to show an overview of the system crashes and exceptions over time and predict them based on their historical relationships with internal quality matrices. Modeling. Our goal was to find a fitting model for software reliability. We we applied two alternative ensemble methods, random forest and extreme gradient boosting. With these methods, we investigated the probability of software bugs related to runtime issues in association with the structural properties of software code as well as the amount of type of software changes along the software's evaluation. The analysis provided two outcomes: relevancy of individual matrices as predictors of external quality, and a quality model that captures qualitatively dependencies between the most relevant matrices and the external quality. Deployment. The deployed models were integrated into the QRapids tools for guiding software developers regarding the predicted evolution of external quality, or to give the indication for the most relevant factors influencing it. Data-driven prioritization of code finding. Business understanding. Detecting code defects is in the earlier stages of software development not only decreases the cost of the software but also increases quality by decreasing the technical depth and the propagation of errors to other phases. With 20 to 30% of all software containing 40 to 60% of all defects. Static code analysis has been shown to reduce post-release failures by more than 50% and thus cut development cost by 20 to 30%. It doesn't replace other verification and validation steps but helps remove certain defect types that otherwise wouldn't be found. However, the warning reports by different statistic analysis tools do not present and defects in order to prioritize according to the critical of software moduling but according to predefined hard-coded defect priorities. Thank you.